Hi all. We are almost at the end of a long and hopefully insightful day. But before we wrap up, we have a short, fun case study from Expedia that looks at tackling an age-old problem about achieving cloud cost savings without compromising reliability. So this is a story of the opposites, FinOps and platform engineering, two teams with very different priorities. But more importantly, it's about what happens when they stop working in silos, start collaborating, and turn that tension between the two teams into powerful synergies. So a quick intro of us both. I am Aditya. I have been a part of Expedia from the last 4 years, and I am primarily in the DevOps and the platform space. I have been working on the cloud cost optimization activities on and off for the last 2.5 years now. And accompanying me today is my teammate, Mohit.
Hello everyone, I'm Mohit. I'm a platform engineer at Expedia Group. I've been here for around 2.5 years, focusing platform engineering, and very much excited to be here and share our journey. I hope you guys will be able to relate the challenges which we have faced and how the cost optimization we have achieved in a large-scale Kubernetes clusters. Thank you everyone. Aditya.
So here's a quick look at what we'll cover today. So we'll start off with the cost reliability disconnect. This is the classic tension between FinOps and platform engineering, where optimizing one often impacts the other. Then we'll take a look at the case study that we performed at Expedia at scale. From there, we'll walk through 3 practical patterns. First being establishing baselines and views. The second being revisiting the legacy, and the third being embracing re-architecture. So we'll go through each one of these in detail through our presentation. And finally, we'll take a look at the key takeaways from our presentation and open up for the Q&A session. Then the cost reliability disconnect. So modern platforms are far from simple infra layers. What we are really operating now is infra at a massive scale. So hundreds of Kubernetes clusters running thousands of workloads spread across multiple regions and multiple business domains. And everything is constantly changing with continuous deployments and dynamic scaling. But the complexity doesn't stop at the infra layer. It extends into operations. Platform teams are responsible for ensuring reliability and uptime, while also managing capacity and scaling behavior in real time. At the same time, they are expected to respond to incidents quickly and maintain strict SLAs, SLOs across multiple teams. So what we end up with is a very highly complex, highly dynamic system where every decision has a ripple effect across cost, performance, scale, everything. And that's exactly where the tension between FinOps and platform engineering begins. So at a very high level, it's the organizational structural difference where the challenge begins. On one side, we have platform engineering. These teams build and operate infra, manage clusters and capacity, and ultimately responsible for managing the reliability and their uptime. They deeply understand the workload behavior and how these systems scale. And on the other side, we have FinOps, or the finance teams. They analyze billing data, generate cost reports, and focus on identifying opportunities to reduce cost spend and improve efficiency. Individually, both functions are doing exactly what they're supposed to do, but the challenge lies in their priorities. Platform teams naturally optimize for reliability, performance, and stability, often adding buffer to their platforms, while the FinOps or the finance teams prefer to focus more on reducing resource usage, staying within the budgets, and maximizing efficiency. So this is where things start to get risky or tricky. Cloud cost optimization, when executed without fully understanding the system behavior, can often lead to reliability issues. If you look at common optimization actions, like things like aggressive pod resource right-sizing, lowering auto-scaling limits, or even changing instance types, they seem perfectly reasonable from a cost perspective, but the consequences can be significant. you may start seeing increased resource contention, latency spikes, and more frequent incidents. And these aren't just theoretical, they show up in very real scenarios. For example, CPU throttling during traffic burst, or auto-scaling not keeping up with the demand, or reduced redundancy increasing the risk of failures. So the key point here is optimization without context can do more harm than good. So we saw the problem, but how can platform engineers step up to fix this lack of context? Cost efficiency is often treated as a separate function owned by FinOps, even though platform engineers actually have the deepest understanding of how their systems are working in production. They know how workloads respond to real traffic, how systems scale under pressure, which services need redundancy, and where inefficiencies actually exist. But when cost optimization is done outside of this context, we miss the opportunity to make smarter, safer decisions. Now, when we bring these perspectives together, the outcomes change significantly. Optimization opportunities are identified using real platform insights, not just the billing data. Infra waste is reduced in a more targeted and an automated way. And most importantly, platforms are designed to balance both reliability with the cost aspect, instead of trading one against the another. And that's the key here. Cost efficiency shouldn't be an afterthought or an external process. It needs to be built into platform engineering itself. Now that we have looked at the problem and where the disconnect comes from between the platform teams and the FinOps, let's make this real with a case study. So for this, let me introduce you to EG's Runtime Compute Platform, or simply RCP. So Runtime is the name of our team, and RCP is an in-house built platform at EG. So it is basically a multi-tenant Kubernetes-based container orchestration platform, and it operates at an incredible scale. So we have hundreds of clusters running in the platform spread across multiple regions, and we have thousands of applications running across thousands of nodes within the platform. So when we started this journey, we started to see some clear, repeatable patterns emerge, things that consistently helped us unlock efficiency without compromising the reliability. The first is establishing views and baselines. So optimization starts with visibility, understanding costs per workload, utilization patterns, and what normal actually looks like. Without that, you are essentially guessing. The second is revisiting the legacy. So over time, systems accumulate decisions like static node pools or oversized instances or excessive buffers. These were often made for good reasons, but revisiting them with current cost context often reveals hidden inefficiencies within the system. And the third is embracing re-architecture without fear. Sometimes incremental tuning isn't just enough. Real gains come from structural changes, like consolidating workloads, optimizing instance families, or even redesigning parts of the infra. And the key here is these changes aren't really about trading reliability for cost. They are about achieving both in a more sustainable way. So let's start with the first pattern here, which is establishing views and baselines. So this is where everything begins. Before making any optimization decision, we need a clear understanding of how our platform is actually behaving, both from a cost and a utilization perspective. Because without that foundation, any optimization is essentially a guesswork. So the first challenge that one may run into is something that we call the visibility problem. So most platforms today have good, strong observability when it comes to reliability. That is metrics, logs, alerts. All of that is well understood. But when it comes to costing, that same level of visibility is often missing. One can see many gaps here, So there might not be a straightforward way to understand which clusters are driving costs or which teams or workloads are actually consuming resources. And more importantly, there are no well-defined baselines for what normal usage or efficiency looked like. On top of that, cost attribution could be a major challenge in shared infra. So we need a way to distribute costs for each of the workloads that might be running in a specific cluster so that the teams who own those applications have visibility into how much they are consuming in terms of the resources itself. So in our case, we had a lot of pieces at the right place. So FinOps gave us clear visibility into how much we are spending, where the spend was happening, and how it was changing over time. At the same time, we, as platform engineers, also had a good understanding of our system. So we knew how workloads scaled in our platform, where we kept buffer for reliability, and why certain clusters were sized the way they are. So both sides were doing their job well. The opportunity was in connecting these two sides. So once we brought these two perspectives together, things started to click. And that made a big difference for us. So once we had the visibility into costs, we felt confident. It finally seemed like we had everything we needed to start optimizing. But very quickly, we ran into another realization. We could see the numbers, but we didn't really understand what those numbers mean. So I remember looking at one specific cluster which was running at 35% efficiency in terms of CPU. At first glance, it looked very inefficient, but then the question came up, is it actually waste, or was it done intentionally with, prior to by the previous team itself? So since in distributed systems, things are not that simple. We can't really aim for 100% utilization in our systems. And we always need to keep extra capacity for a reason. So there can be traffic spikes, there can be node failures, deployments, or even rescheduling. So we need to cater to each of these decisions or scenarios before we look at how much buffer we need to provide to a specific cluster or an application itself. So in this scenario as well, 35% didn't look obviously wrong anymore. And that's when it clicked for us. The problem wasn't just visibility. The problem was visibility without context. So we needed to understand what normal actually looks like for us. And that's where baselines came in. So we started defining what healthy actually looks like, how much utilization is expected, how much buffer is actually needed, and when should the system scale. So once we had all of that, everything changed. Now, when we looked at a cluster, we didn't just see a number, we understood it. And we could say this is below the baseline, probably over-provisioned. This is within the range. Let's call it healthy and end the day. And if it was too high, we might be looking at a potential incident or a risk. And for the first time, optimization felt safe for us. We were no longer guessing, and we started making decisions with confidence. Now, I request Mohit to take over for the rest of the slides.
Thank you, Aditya, for briefly explaining about FinOps and platform engineering. Now, this is one of the most important at Expedia, which we have done by revisiting the legacy, which nobody wants to talk about. After improving visibility and establishing baselines, we turned our focus to something often overlooked, our existing systems, because sometimes the biggest opportunity for cost savings are not in the new optimization, but in rethinking what we already have. Let me start with something that we can all relate to, legacy waste patterns. Most platforms are not built from the scratch. They grow over time, step by step, and every decision made in the past are usually not the right one at that time. For example, we generally add extra capacity to handle traffic spikes. We increase the node size to avoid outages. We kept auto-scaling conservative to stay safe. All of this was done to improve reliability. But over the time, things change. Workloads evolve, traffic becomes more stable, auto-scaling gets better. However, the old configuration often stay the same. And that's where the problem starts. These decisions are not wrong, but they just don't get revisited. And over time, this leads to hidden inefficiencies. Some common areas where we saw most of the cost waste, idle cluster capacity. Sometimes the minimum number of nodes was set too high even when it's not needed. Oversized compute, we continue using largest instance types that made sense earlier but now are no longer optimal. Sometimes we override reliability, like spreading every workload across multiple AZs and nodes, even when it's not required. Now, once we identified those legacy inefficiencies, the next challenge was how to address them safely, because the reality is no one wants to touch production systems that are already working. There is always a fear that changing something might introduce stability, impact performance, or cause outages. So the goal was not just to optimize, it was to optimize without risk. To approach optimization safely, we started by looking at the historical data. We analyzed the CPU and the memory uses over time, peak traffics, patterns, and how much headroom are actually needed. This helps to understand what normally really looks like. Based on this, we identify safe optimization opportunity. We focused on right-sizing instance types, reducing unnecessary buffer capacity, and improving workload density on the nodes. But the key was how we implemented these changes. We didn't do everything at once. We followed a gradual approach, starting with controlled experiment, rolling out changes in phases, and continuously monitoring the impact. We didn't remove capacity, we removed unnecessary assumptions, and that helped us to reduce the cost of our infrastructure. After revisiting the legacy configuration and establishing visibility, the next step is recognizing that some of the largest efficiency gains require structural changes to the platform. These are not simple configuration tweaks, they involve rethinking how infrastructure is designed and used. Many organizations avoid these changes because they appear risky or complex. However, when executed carefully, they can unlock significant cost reduction while improving platform efficiencies. First optimization that we performed was with the GPU node provisioning in our platform. Expensive categories like G and P in EC2s were enabled in the general node pool, causing Carpenter to provision even though there were no pods requesting GPUs. The other problem with this was cost attribution and forecasting. Apps pods not using a GPU should not pay for the GPU. To solve this, we removed all the expensive categories from our node pools and kept just one single node pool for the GPUs. It was a one-time complex migration effort, but it was worth every penny. Our second major optimization focused on our platform data clusters where batch jobs were running without proper control and impacting overall efficiency. We all heard about the Spark jobs costing too much money on the platform. But we have identified Spark jobs were configured to run on the general node pool, which is common for all the apps, including latency-sensitive apps. Carpenter runs continuously uncontrolled cycles of a consolidation where it selects a node for disruption and deprovisions it. Provisions a new node and repeats the same cycle again. This caused huge pod churn in the cluster. To prevent pod churn, Spark teams ended up using the do not disrupt annotation. This annotation uses is an anti-pattern to consolidation, and we can understand this is using a simple deprovisioning example where we have node n with a Spark node with this annotation. Carpenter marked this node for replacement or the consolidation due to its internal algorithm. Node is drained completely, but however one pod remains. This pod is the same Spark pod, which continue to run till eternity until itself gets completed. The problem may sound complex, but the solution was the simplest. We moved all batch streaming jobs to a separate node pool, turned off the consolidation of that particular node pool, and the result, even though expected, shocked us all. That optimization led our average node count from average 600 to average 300. Monthly cost almost got halved, and we have a data platform that now streamlined, efficient, and built for scale. Here, the third structural changes were focused on the NOPT optimization. Sometimes small platform change can have a significant impact on overall system efficiency, where we did instance optimization, implemented min domains, and the fixed TTL of the Carpenter. Instance optimization, we moved our workload to a newer generation instances. This is not only improved performance, but also help us take advantage of the better price to performance ratios. It also allowed us to adopt newer technology while reducing overall infrastructure cost. Min domain related to the AZ balancing. With EKS 1.28, we gained native support for the availability zero balancing through the min domain feature. Before this, we relied to our custom built scheduler called general topology fixer to maintain node balance across multiple AZs. After adopting min domains, we were able to decommission the custom solution, and the overall overhead has been reduced. Fixed TTL in Carpenter. We configured a node TTL of 20 days and added a 2-day termination grace period. Previously, some nodes would get stuck due to the problematic prods and required manual intervention. With this change, node lifecycle management more become predictable and automated, reducing manual efforts and avoiding long-lived inefficiencies. The fourth structural and workload optimization focused on reducing the service mesh pod count. Istio is a core part of our platform. It runs as a part of a service mesh across all clusters, so any inefficiency here has a direct cost impact. The problem is with how we were scaling Istio. We were scaling Istio where the number of replicas was fixed on the basis of the cluster, sometimes ranging from 10 to even 100 of the pods of the Istio. This approach was safe but not efficient. It didn't reflect real-time demand. So what we have done, we started using custom auto-scaling using KEDA. Instead of scaling based on the static numbers, we started using the pilot XGS metric from the Prometheus to drive scaling. This allowed Istio to scale based on the actual load. The result was significant from this optimization. We reduced the number of Istio by almost 50% in our platform, while still maintaining performance and reliability. Finally, to conclude, one key learning from this initiative that cost efficiency is just not a FinOps problem, it is a platform responsibility. FinOps help us to understand where we are spending, while platform engineering understand why and how to optimize it safely. So that's a conclusion which we derived from our initiative. That's all from our side. Thank you for your time. We will be here for the questions if you guys have any. Thank you.